Alright, so here's your question. The half-life of a radioactive uranium-2 is 245,500 years. What percentage of the present amount of radioactive uranium-2 will remain after 5,000 years? Alright, so any question like this, whether it's radioactive growth or radioactive, or doesn't have to be radioactive, but exponential growth or exponential decay, comes back to this equation here, which is A is equal to A0 e to the kt, where this A here is your initial amount. So, or not your initial amount, I'm sorry. This is your current amount, whatever amount that you have at some specific time t. So after 1,000 years, you'll have some amount of uranium, or whatever it is that you're dealing with. This A0 right here, this value here, is talking about the initial amount of uranium. So if you have 1 pound of uranium at the very beginning, this is what goes into here is 1 pound, or however much you have, doesn't matter. And then after some amount of time, say after a year or so, say you only have half a pound of uranium. So that'll be the current amount of uranium that you have after some amount of time t. E, we all know that's the value 1728. So that's normal. K is your value that you're kind of, this really controls the entire equation here. K is a constant that if it's negative, that means that your entire equation is showing decay. If it's positive, your entire equation is showing growth. That's really all that does. It determines where this thing is going to go. And then, of course, t is just time. Alright, so for this equation here, let's go ahead and go to red. Alright, for this equation here, for this problem here, it really only cares about a percentage after some half-life or some time. Now, the time that it gives you is 5,000. We'll get to that in a little bit. But for right now, the numbers that we care about are half-life and 245,500 years. Alright, so first we'll begin with, say our initial amount is 2. We don't really care. All we care about is that our initial amount is 2, and after some time it's 1. And we get these numbers because if we have some initial amount 2, or just any initial amount, and we're looking at the half-life up here, we just want this to be half, this number here to be half of this one. We don't care about anything else, just the ratio between the two, especially because we only care about percentage. We'll care more about this number in a little bit, but really right now we just care about the ratio between the two. So to make it simple, we just call them 1 and 2. Alright, and then after that we have E, K, we don't know K, we're going to try and solve for K, and then T. So I don't really feel like writing out T, or this number a whole bunch of times, but we just know that T is going to be equal to 245,500. Alright, so I don't feel like rewriting that. So anyway, so now to solve for K, so what we do is 1 divided by 2 equals e to the kt. I just brought over the 2, natural log of both sides to get rid of this e. So natural log of 1 over 2 is equal to kt. Alright, so again, we're looking for k. We have t, it's up here. Let's divide t to both sides. So now we end up with the natural log of 1/2 over t is equal to some number k. Alright, so now we're going to solve for k. Get our handy dandy calculator. We're going to do 0.5, and the natural log of 0.5, so that's just this part right here. Natural log of 0.5, some crazy number. And this number divided by t, which again is the 245,500. Now this gives us negative 2.823 whatever, and it's important to note the 10 to the negative 6th here. Okay, that'll be really important. So move that to the side so I can write this down. So k is equal to negative 2, we'll go ahead and just call this negative 2.823 times 10 to the negative 6th. Alright, because that'll be really important. So now we solved k. Right, this is the really big deal right now. This is like the middle part of the equation, or the entire problem. Alright, so let's go ahead and change colors here, something like green. Alright, so now this is the second part of the problem. What percentage? So what percentage? Because we're dealing with percentage, we're going to go ahead and set a 0 equal to 100%. Alright, so we start off with some initial amount, 100. We don't care because we just want it to be percent. That's all we really care about right now. Alright, and go back over here. So we have a 0, k, we know k. K is negative 2.823 times 10 to the negative 6th. Alright, and t is right here. T is 5,000 years because it wants to know what percent of the radioactive material we have after 5,000 years. So T will be equal to 5,000. Alright, so we can just go ahead and throw all this into our equation here. A 0, so we're just going back to this guy over here. A 0 is going to be 100 times e to the k. I don't feel like writing these numbers down again, so I'm just going to go kt. Alright, so this will be equal to our amount, A. Now this amount isn't really going to be amount like a weight or anything like that, because again right here we just have 100, which is just 100%. Alright, so we only care that it's a percent. So A is going to give us a percent. So again, we'll go ahead and throw this into the calculator. Alright, so we have E. E doesn't look like it's on here, so we'll just go ahead and do 2.718281828, and yes, that's e to 9 decimal places. I just have that memorized. Times time, no, sorry, not times, raised to the power of, now this is where we use this number here, negative 2.8. So we have 2.823, that's going to be negative, and this will be times 10, this will be raised to the power of negative 6. Okay, so this right here is just negative 2.823 times 10 to the negative 6. That's just this k value, so we've only done k. Now times 5,000, because we want to get the time in there. 5,000. Alright, go ahead and close our parentheses. So now this number here is just this portion here. So this is going to be negative. This is our k times time. So go ahead and get equals. So now we have A is going to be equal to, A is going to be equal to right here. So we started off with 100. So after 5,000 years, being that we started with 100, this is actually a percent. So this is going to be 98%, so 98.5%. So A is going to be 98.5%. Now let's make sure this makes sense. Let's make sure that this number right here makes sense. If the half-life is something massive, this is 250,000 years right here. This is 250,000 years, just about 250,000 years. So if we're only going to hit 5,000 years, if we're only going to see how much radioactive material we have after 5,000 years, it really does make sense that it is 98.5%. Alright, so that's the entire problem. Good luck on your homework.